I'm extremely excited to be here because data is such a hot topic right now, and I love panels because it's also an opportunity for me to learn. So in addition to researching my co-panelists here, I'm really excited just for what we're going to find out today. There are some things, data is obviously at the forefront of everything that's going on in AI. Quick show of hands, who in the room is a data geek?
Yeah.
Okay, and everyone who doesn't have their hand up, who didn't just have their hand up, you are probably interested in data because you're aware of what a huge impact it's having in what AI has been able to emerge into, and how it's really at the forefront of what's making breakthroughs in the field. So I'm excited to hear from these two. I'm going to let them introduce themselves. As a quick intro on me, I started Lincoln Group about 15 years ago, which we sold a defense technology company, which is one of the first to use AI for machine translation and large language analysis. Then I was at MIT as a researcher, and really a love of lifelong learning. And now doing board advisor work with startups, all completely outside of the field of computers, in the field of new aviation. And also a co-founder of Squawk AI, which is helping companies to interview experts to pull useful information out of them. Yaniv, give us a quick intro.
Yeah, I'm Yaniv, founder and CEO of Alpha Biome. I'm also a researcher at MIT, and for the past 20 years, I was trying to look at how AI can be used to find order in the chaos, mostly working in defense and finance. Until a few years ago, I discovered that using the same techniques, we can start making order and discoveries in genetics. Started the company where we built a platform that can analyze trillions of data fragments and revolutionize the way we discover biomarkers that are very useful to personalized medicine and drug efficacy, performance, and so on.
Great, and Gunnar?
So I'm Gunnar Carlson. I'm a professor of math, retired at Stanford, and also a founder and CTO of Blue Light AI, which is a company doing interpretable AI. So I started out life as a pure mathematician, working very hard at that. About the year 2000, I realized that some of the things I was doing, which was related to the mathematics of shape, called topology, had implications for big data and understanding large data sets. So that led to many grants, also the founding of a company in 2008, which ultimately was acquired in 2019 as we developed the technology further. I realized, though, that we left a lot on the table in that company, and that the topological, the shape of data, has even more implications and is even more useful in AI than it was in just the straight-up big data space. So that's why I'm so excited about the way things are going now.
Well, this is actually, it's a great segue hearing their intros. These two are heretics in some way. A lot of the world has fallen into the belief that all we need is more data. We need bigger data centers. We need the $1 trillion data center in Texas. We need bigger chips. We need more NVIDIA H100s. And these two both believe that that's not going to be enough, that that's just going to be, just scaling up data is going to be a dead end, and we actually need to understand more the structure and the shape of the data. So we're going to dig into that today. Let me ask you both from your own perspective, just to kick that off, to sort of frame for us to encapsulate why you think merely throwing more data at the AI problem is not enough.
Because sometimes there simply isn't enough data. And I think that it all stems from the fact that LLMs are so successful. I used to give talks in many forums to teach people about AI, and I used to start with the Turing test. And I said, yeah, you know, the Turing test is something that we are so far from achieving. A computer would never be able to fool a human being that is speaking with another human being, and then we just, zoom past this achievement. And this is, I think, because there is a lot of textual data. There wasn't the right technology. the transformers were invented and implemented, and suddenly we got it, and then people thought, so let's just take and deploy it on anything else. But and this is actually not the case, and probably language might be a simpler problem than many other things for which we may require much more data that we simply don't have. So I think that this is one of the reasons.
Just to double click on that before we move on to Gunnar, you said that we've kind of reached this plateau in some things that we're seeing that probably, who in the room has played with Nano Banana or seen something else? Nano Banana? So that's an incredible leap from what we had a year ago. So we're still seeing progress in certain areas. What are some of the specific areas where you see that the more data is a dead end?
For example, genetics. We don't have enough data. We actually collected a repository of a few thousands of genetic samples that we actually acquired and collected. And this is one of the largest data sets around. And it's still relatively small if you just use it as a plain data and try to LLM it without trying to introduce some more higher level or high dimension order in this chaos, which I think that I'll let Gunnar elaborate on, given that I know that you have a more intelligent thing to say about it.
Okay, yeah, so I would want to talk a little bit here about the implications for how we do AI of this understanding, because I totally agree that the data is fundamental. The point is, usually when we're talking about specialized tasks, and I think that it's so critical, that is this notion of post-training, which means specializing your AI, perhaps using a foundational model, perhaps not, but specializing it, it is the future. That is the interesting thing. And then the reality is we're not going to have enough data almost ever, and it's going to be very expensive to get when we can. So I would like to argue for what does this mean about the way that we do AI? And so in thinking about AI, you can kind of think of it as a three-part process. There's the data, which is the input. There's the model itself. And then there's the output, which is some transformation of the internal state of the model. And you can modify, do fine-tuning at all three levels. That is to say, you can do fine-tuning based on the data. You can hope to get inside the internals of the LLM and start to poke around. And you can also, fiddle with the output. And I would want to argue for saying most of the time we should be doing the first. That is to say, we should be doing smart transformation. I would say it's kind of a more traditional word is signal processing, where you say you kind of modify the data. We need generalized signal processing for doing these problems with LLMs and generative AI, and that we ought to focus on that. And the idea that one can get inside the neural net, I think we should be trying to understand it, but we're far enough away that if we get in there and poke around, it's going to be very unpredictable what happens.
And this is a controversial take. So, the frontier models, Anthropic, Google, OpenAI, they haven't done very much of the first thing. They have taken these huge corpuses of unstructured data, including sometimes pirated books of all the books that were ever published, and just thrown that in the pre-training. And what's being talked about here is maybe some pre-training or pre-annotation, pre-training annotation. And you're talking, I think the two of you can come at it from different angles and talk about how that might be valuable, Yaniv, in your context for making AI make predictions about genetic data or small fragments, and Gunnar, from your standpoint about making science or making breakthroughs in science.
Mm-hmm. So in genetics, I think that what domain experts are trying to do is do a bottom-up approach. They have this toolbox of things that we already know. We know that three nucleotides encode an amino acid, and a bunch of amino acids create a protein, and we know some things about folding, and we know some things that proteins do. And from this, they're trying to explain the world. And I call it looking for what makes sense. We do a completely alternative approach, which is looking for what doesn't make sense. I'm not trying to constrain us to what we already know about or think we know about how the world works. We just look at all the data, all this chaos, and try to find things that simply don't make sense. And these signals are actually the important things that we should be looking for. So we should be investing in the development of a really robust, smart, strong signal detection mechanism. And to Gunner's previous point, of course, the risk in doing that is introducing some bias. Because if we try to featureize or to introduce signals, then there might be some bias that we introduce to the system. And then we should, of course, try to find the right balance, perhaps letting specialized AI find these mechanisms that detect signals and introduce them back. I don't know. This may be an interesting approach. So yeah, this is.
Can you, just before we go on to Gunnar, can you explain that to me a little bit, how you would find that signal and feed that signal to the AI? So take your specific, what your company's doing with microbiome DNA analysis. What's an example of, and you said you're looking for signal to explain exceptions. What's an example of something you would find, and how would you annotate it and feed it to the AI?
As I said, for many years at MIT, working with Professor Pentland here, we were looking on behavioral data, how communication system work, the blockchain, cyber. And what we found out was that there are recurring patterns that emerge in any such data that has to do with temporal changes, the temporal dynamics of human activities. And then we were looking at genetics. And in genetics, when I look at the genome, of course, there isn't a temporal element, but there is a spatial element. If you look at it as a very long linear string, you can look at the reoccurrence of substrings and try to come up with interestingly similar, same mathematical equations that describe those that are almost identical to the way many temporal systems behave. So if you have this equation, it's basically agnostic to the data. You can now start sequencing microbial DNA, animal DNA, plant, soil, air, germs from the air, not the air itself. And then you already know how this data should behave.
So you're feeding the AI not just the data, but the data plus this equation
exactly.
that you determined. Okay.
Exactly.
And Gunnar, do you want to talk from your context for discovering in science, how you think?
Yeah. So I'm thinking, you know, the role of AI in science, I think, is maybe fundamentally different from its role, or at least from parts of its role in the commercial world. The commercial world sometimes simply wants a prediction, you know, a risk for something. And in science, we're looking for insights. And what that means is that, you know, the models that we build, you know, if we're going to optimize something, that's not directly of interest. What might be of interest is the features that are generated inside. So by features here, I mean the activation patterns inside a neural net. So one needs to understand those to extract insights. What's really interesting, and it took me a long time to sort of get this, is that although for most AI, we optimize something, but we don't care about what it is that we're optimizing. We're just interested in what the machine has to do to optimize it. So if you think of a large language model, they're usually built so as to be able to predict the next word. After you've got a sequence, you've got the next word. No one cares about the next word, except maybe if you're in a translation task, but you know, most of these conversational tasks, no one cares about the next word, they care about the whole thing. And so instead, what's true is we care about what the machine had to do to be able to get to that point. And that's kind of that's kind of a new thing. I'm not sure that there's been that we've ever seen that in the course of science before. But anyway, what I would want to argue is that it's a fundamental role to be played in sort of compressing and understanding the features that are inside a neural net. And by the way, it's not just science where it's that. If you start thinking about it, you know, our company has worked with, you know, kind of fraud data and so on, and there too, people aren't always wanting just a straight up prediction of fraud. They sometimes, they have analysts who are smart, but the analysts want to have new features to look at, sort of, you know, I think in Don Rumsfeld's terms, you know, unknown unknowns. Find the unknown unknowns in your problem.
Well, there's two threads I want to pick up on there. One is the concept that progress in science comes through new explanatory knowledge. But the other one, let's just stop there, is unknown unknowns, because this is a big topic in AI, and the one that you're all familiar with. Who's taken a Waymo in the room? There were so many of them running around the Google site yesterday. It was kind of like living in the future, seeing so many driverless cars going by. The reason why Waymo isn't everywhere today is because of edge cases. And Waymo can drive better than a human, can drive better than anyone in this room on some given tasks. But all of us in this room, the weakest driver in this room, could do better than Waymo at some edge cases. And those are also kind of unknown unknowns. How can looking at the shape of data help us to understand? And is there an example from either of your work where you've been able to feed in something, or is there something tantalizing that you see out in the future?
Let me give an interesting example maybe here. And it's not quite toward the Waymo thing, but I always wondered, can we input something into a large language model or even a small language model that will tell you something about the syntax before you ever get to understanding the semantics, which is what's inside. And so what we did is we built a neural network that predicts next part of speech instead of next word. And that's a much smaller problem. It can be done very quickly. And then you can take the features that were generated in that and feed it, allow it to act with the input to a language model, a fairly small language model. And what we found was that we got a 15% reduction in perplexity, which is a measure within those large language models of vulnerability to hallucination. So I think that's sort of an example of sort of saying, let's think about what's possible in this data. What features are possible? Let's play with them and let's understand them. Let's not insist that the model has to find it. Maybe we can give the model some help. After all, when kids are learning in school, we certainly give them help. And we find that it's hard to get them to do specialized tasks. I would recall my 6-year-old's challenges with the multiplication table. But so in any case, that why should we not be helping out with the specialized task when we know that's what we know best? We know what we want, and we should be doing the features to that.
So it's introducing common sense.
Yeah.
Mm-hmm. And then when you ask Claude to help you write some code, you wouldn't be getting some nice emojis in the comments.
Well, that's it. Actually, you gave me a really good example earlier, Gunnar, of a self-driving car that didn't see, misrecognized a sidewalk because it saw a part of the stripe, but couldn't infer from that when you see part of a stripe like that, it means that there is a sidewalk. And we talked about how that's a common sense model of the world that even a toddler would have. There's a colleague of Sandy Pentland's at MIT who's in brain and cognitive sciences who's done really interesting work in studying how children learn and build these mental models, and had a promising path that I thought very promising when I was there 10 years ago, of combining physics models and from gaming that he would get from gaming engines with AIs to try to actually bring that common sense to AIs. And unfortunately, it seems like just the raw big data approach of OpenAI has actually won out. But you still see promise in the shape, in looking at the shape and in this sort of pre-labeling. As a way of maybe introducing that common sense.
Well, if you understand the shape of the data, you may, for example, see, a long line coming out, and you wonder what's at the tip of that line. You can also color the shape, by, say, accidents or mispredictions. So, it allows you to localize it where it's happening. And I think there's a fundamental thing here. Sometimes it goes under the heading of clustering, but it's really much more than that. It is the notion that we need to start understanding meaningful groups in the data, and we need to understand their explanations. It's a little bit analogous to, I don't know if any of you have played the game Connections in the New York Times. What that insists that you do is you are supposed to identify groups in the data that have coherent, and then also provide explanations for them. And that game, that's the analog to what we need to do in data science. We need to understand what are the significant groups in our data, and then the shape becomes fundamentally important because it tells you it's not this massive collection of data, but it's organized in some fashion, a little bit like a knowledge graph.
And actually, this can still be unbiased, because if learning the topology is done in a generic way, it would accelerate everything that happens afterwards without any bias introduced by us.
And the topology that we're talking about, it's interesting that your career has spanned very pure academic, pure math, through to applications. But topology used to be considered one of the most pure fields, and now it's very applied. Just at a high level, to give us all some context, a traditional way you might describe a star field is just a mass of distances and coordinates, but your approach is to try to actually move to maybe see a constellation, to describe.
It's correct. Well, what I would say is that there are two things there. There are coordinates and there are distances. And topology fundamentally says, I don't know the coordinates, but maybe I know the distances. And so what can I rebuild just from knowing the distances? And it turns out that it's a lot. Now, it's a little fuzzier than that because actually, even certain configurations of distances will be similar to others, and so. But fundamentally, it's definitely independent of the coordination. It was one of the big motivations for starting the subject in the first place.
And Yaniv, I want to ask you at AlphaBiome, Gunnar mentioned this going back clustering, and you mentioned going back and forth between like a visual representation, then back into the code. To what extent have you and your human colleagues at AlphaBiome had the computers generate something visual that you then got insights from that you then used to refine algorithms?
I always like to see the data and actually feel it and touch it. And this is what I always teach people I work with. You have to actually feel the data firsthand. But I never let it interfere with the necessity to make sure that everything is unbiased. So I like to feel it, but I don't want the machine to know what I think I know about the data. So the machine should do what it's doing, and I'm understanding or think I'm understanding what I'm understanding, and we should work separately.
Okay. And to what extent do you use that process of having the computers give you some visual data, and then you in your group meeting looking at visual data and using that to inform how you feed back to the computers? I
think the challenge for us actually is we need to go beyond just visualization. It's extremely useful, and you can do it with point and click methods. But we need to start automating that process more. So we've automated the construction to a certain extent, but we're going to need to modify those constructions. To Yaniv's point, I think there are actually lots of ways of extracting shape from data that you can do. So from my point of view, that's the challenge, making this a bit more automatic. And so being able to take something like this, the model, and say, well, what does this imply? Maybe we use an LLM and get a conversational interface with this, so that you can get a report of your data that just as a starting point, and then you can sort of query it, and ask more specific questions as you go. But it needs to be made easier. What we found in our first company was that point and click was something that was good for a certain population of people. But it really wasn't enough. You needed to automate it more. LLMs weren't available then, but now they are.
And Palantir built a multi-billion-dollar value company on the strength of that insight.
Well, that's true.
To make the analytics easier. Well, in wrapping up, I want to mention the book that's maybe had the biggest influence on me in the last 3 decades of my life is The Beginning of Infinity by David Deutsch, and he has an argument in there about how science will be very hard for AIs to do, because science really fundamentally consists of developing new explanatory theories, new explanatory models that can then be validated by experiments, rather than looking at the experiments and all that data and sort of inferring the explanation. What are some of your insights around how these approaches of looking for patterns, looking for shape, might help us actually make some breakthroughs with AI in science.
I was actually just this morning spending almost an hour arguing with GPT-5 about the proper way to analyze some problem, and he made some really convincing argument, and I didn't want to just overrule and say, no, you should do it. I tried to really convince him, and until I got his conviction that the way I'm seeing it is the right way, and said, okay, assuming that, this and that, it's fine that you use these assumptions. So I think that we should really soon be looking at some really innovative, let's call it a Turing test for scientists and math professors and AI professors problem. Don't know when it's going to be, but not so far.
I love it. Maybe the one thing that comes out of this is we redefine the Turing test as making some breakthroughs in science. Yeah. Your thoughts on that?
Yeah, so for me, I think that the breakthrough comes from coming in two directions. Building something that's more and more powerful so that it detects more and more things, but on the other hand, is easier to interact with so that you can extract the insights. So, you can build something very powerful, but if it requires a PhD in engineering or statistics or whatever to get the information out, maybe that's okay for your situation, but really we want to get it so that it makes it easier for people to do. And so I think one needs both that interface. So it's a trade-off usually between the power of the technique and the accessibility of it to others.
Fantastic. Well, they didn't provide us enough time with questions today, Yaniv and Gunnar and I will be around all day. We'll be around outside after the session. And we would love to interact with all of you. And we're all very easily findable on LinkedIn. So thank you for your active listening.